George Frederick Bernard Riemann was a great German mathematician, considered to be one of the greatest and most important mathematicians of all time. I present him to you right now. The theories he introduced revolutionized geometry, number theory, and complex analysis for years to come. Riemann was born into a poor Lutheran family in 1826. We'll calculate for money. It's tragic. Riemann entered the University of Göttingen for theology. But after his mathematical genius became apparent, he transferred to the field of math in the University of Berlin. Very studious, studying his equations. After graduating from the University of Berlin, Riemann worked through numerous odd jobs before he could finally find steady work as a professor. Hard work. He did a lot of hard work before he got his job as a professor. As professor, he gave lectures in Riemann geometry and eventually was given the position of head of the mathematics department. It was during this time that Riemann made the most advancements in complex analysis and geometry. He would eventually pass away from tuberculosis in July of 1866. Mathematician Augustin Cauchy gave us the modern definition of continuity and defined a definite integral as a limit of a sum. Riemann then took this and created a theory where shapes are used to approximate the area under a curve. Riemann sums can be done using a left approximation, a right approximation, a trapezoidal approximation, and a midpoint approximation. So we're going to do a quick example for all the problems for each of those four. And for the sake of keeping it consistent, we're going to use the equation f of x is equal to negative x squared plus 4. So, here you can see the graph. This is for the left Riemann sum. So you want to put it on the left side of the board, right? Yep. So, we have the same graph. We have a graph here from negative x squared plus 4 from 0 to 2. So we're going to find the area using a Riemann sum from 0 to 2. Approximation. We're going to approximate the sum right here. So what we want to do is create these rectangles. So you can see I made a rectangle here, another one here, and they go all the way down. There's 4 of them, and they all go by intervals of 1/2.
For the left Riemann sum, you always want to make sure you take the point and then move to the right and go into the next point on the x-axis.
Because what you're going to do is you're going to take the area of all those rectangles and add them together to get your approximation. So you want to get the height of the rectangle that's on the left. Yes. That's what yes. You all understand. Good.
Calculus BC terms.
So what we want to do is take the area, like I said, take the area of these 4 rectangles. So we're going to take 1/2, because all these subintervals are 1/2, and we're going to take f of 0, f of 1/2, f of 1, f of 1/2, and not f of 2, because we're only taking the values that are to the left. So we're going to take f of 0, get 4, well, let me write this out. We're going to take f of 0 plus f of 1/2 plus f of 1 plus f of 1/5. So that leaves us 1/2. F of 0 is 4. F of 1/2 is 3.75. F of 1 is 3. And f of 1.5, 1.75. Now from here it's just simple algebra. So it's 1/2 plus 7 plus 5.5 equals 6.25 units squared because you're taking area. So this total of 6.25 is going to give you an over approximation of what the actual sum is. We don't know what the actual sum is, but we know it's an over approximation because we're taking these 4 rectangles here and we have these shaded areas here that aren't actually in it. So we're adding those on too. And you're going to see with the right Riemann sum is going to end up being a under approximation, because instead of taking areas that aren't included into account, you're taking areas that you're not taking areas that are supposed to be included into account. We'll explain how it's done.
Okay, as Sam said, for a right of Riemann's approximation, there are going to be some spaces underneath the curve that are not going to be taken into account by the rectangles. So, like the left Riemann sum, we are going to take the bases of the rectangle and the height of the rectangle, but what's different is we are going to start taking points to the right of the curve and move to the left to connect the rectangles. So as we did here, one here, one here, one here, and one there. So the equation is practically the same, except you are going to not take into account the f of 0 as we are starting from the right. So what it's going to look like is 1/2 times f of 1/2.
F of 1/2.
Yes, f of 1/2 plus f of 1 plus f of 1.5 plus f of 2. Might be a little hard to see, but don't worry about it. Okay, so calculating this all out, you would get 1/2 times f of 1/2. Just work on this, you get 3.75 plus f of 1 would be 3 plus f of 1.5, which is 1.75, and f of 2, which is going to be 0. For a grand total of, if I do my math right, carry the 2, multiply by 5, square root of 77. It's 8.5. It's 8.5. Which is finally going to be 4.5.
So you see how this value and that value, they're not that close to each other. That's because, like we said, this is over approximation, that is an under approximation, meaning the actual area, which we don't know yet, is somewhere between here. And when we do the midpoint approximation and the trapezoidal approximation, which we will do now, you will see that those values are going to be a lot closer to something in the middle that is definitely closer. So now, instead of being on the left or the right, we're going to try to get a midpoint approximation to get something that's a little more accurate to find the area, or approximation of the area. So we still have our 4 subintervals from 0 to 2 of 1/2, 1, 1.5, and 2. Except instead of going to the left or the right, what we're going to do is that we're going to use the points in between all those subintervals as midpoints. So you're going to use 0.25, 0.75, 1.25, and 1.75. So this way, we're not too far to the left, we're not too far to the right, so we're going to get a more accurate approximation. So we're still going to use 1/2 on the outside. But instead of using like f of 0 and f of 1/2, we're going to use those midpoints. So we're going to use f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. Now the values get a little bit messier with the decimals and everything because we're not getting kind of values but midpoints. So I did the math already, and as your answer, when you add it all up, you end up with 5.375 units squared. And that would be your midpoint approximation. Now notice how our previous values for the left and right were 6.25 and 4.25. See how now we're in the middle, because it's going to be more accurate. So now lastly, we're going to do a trapezoidal approximation. So we've used rectangles so far, to do the midpoint, the left, and the right approximations. But now instead we're going to use trapezoids using each of the 4 subintervals. So keep in mind, the area of a trapezoid is 1/2 of B1 plus B2 times the height. So what we're going to do is make 4 trapezoids between each subinterval, and then add all the areas together to get our approximation. So we have them between 0 and 1/2. One half and 1. 1 and 1.5. And 1.5 to 2. So we're going to find the area of all 4 of those. I'm going to write this out to get the area of each trapezoid. So we have 1/2 of f of 0 plus f of 0.5 times the height, and the height of each one is 1/2, because that's our subinterval. It's going to get long. Plus 1/2 times f of 0.5 plus f of 1 1/2 plus 1/2 of f of 1 plus f of 1.5 times 1/2. And the last one, we have 4 trapezoids. 1/2 times f of 1.5 plus f of 2 times 1/2. And the numbers also going to get messy for this one. But when you add it all up, you get 5.25 units. Now this is also in between what the left and the right were, and it's close to what the middle approximation was. And that's because we're trying to get closer and closer to what the actual curve is using the trapezoids. And that's how we get an even closer approximation.